I'm going to begin today by reminding you where my website is. I'm opening a browser and I'm going to science.kennesaw, sciencE.kennesaw.edu /J-Lewin. That's what it is. science.kennesaw.edu /J-Lewin. And when you get there, apart from various other things that are here that may possibly interest you, like the survival guide, there's a 4381 contents. Please go there very frequently. There might be announcements that you need, and I put lecture notes here, and I also put any important announcements that you need. I can tell you now that the lecture notes in the website are probably better than the ones in the CD from last time. I'm a bit worried that I may have I was in such haste and in such a state that I think I may have made some errors. The CD from today will have that corrected and will have today's lecture notes and today's video. Okay, everyone? And the contents document contains a link to the course outline where you can see all the stuff to do with the course. If you haven't been there, please go there. So I'm actually getting ready. Thank you so much for doing that. And so I'm getting ready to start. Let me announce first, it is my policy in the classroom that no one uses any electronic device in my classrooms. That means phones, calculators, various other machines, tablets, computers, but heart pacemakers, I might possibly give you special dispensation if I see you gasping for breath. So anyway, having said that, I'm going to actually get going with our material, and I want to let you know that our material begins the text with chapter 5. Why? Actually, the stuff in the earlier chapters is of very great interest, but the material there is largely included for casual reading on your own and for visiting in little bits when it's needed. It's not possible to read a whole lot of stuff about the principles of mathematical writing except in the context of actually doing mathematics. I personally am against the notion of a course in mathematical writing. You need to do the mathematics, and while doing the mathematics, learn the mathematical writing. And this is, you should actually start in elementary school, and in high school, and in pre-calc, and in Calc 1, and shouldn't suddenly get visited on you when you're in 4381. And since this hasn't happened, because some of you have had what I call my math lab calculus, I shudder even to let those words sully my lips as they come out. The trouble is, I do have a job to teach you some mathematical writing. I started that last time. I gave you the mantra. Let's say it again. To use the fact that something exists, use the word choose. You can't say choose to prove that something exists. How do you prove that something exists? You show an example, whether it's a unicorn or a whatever, okay? Now, to prove a for every statement, and you're going to see this happening a million times, we say suppose. And those are the three cornerstones of mathematical writing, and you will see this happening again and again and again. Okay, chapter 5 introduces the number system. What is all this about? You might say to me, look here, I've had this number system all my life. Or what could you possibly have to say to me that I haven't been told before? I'm going to tell you something. Some of you may have heard this from me in some other courses. I apologize to you if I bore you. Other people have not heard it. It is a standard known principle that the real number system as we know it is thought of as a line of numbers. It's not a big blob of numbers. It's a line of numbers. Do you know why? Because of the less than sign. The less than sign strings the numbers into a line. If the line points from left to right, bigger numbers go to the right of smaller numbers. You understanding me? So here's the point. Every number gets to live on that number line. But have you ever thought about the idea that maybe you could ask whether every point on the number line is occupied by a number? That's a question that they never raised when you were in elementary school or when you were anywhere else, actually. Oh yes, here is 1, here is 2, here is 3, a little bit to the right of 3 is pi, you know. All the numbers that you know get to live on the number line. But if you were to take a point at random on the solid number line, is there a guarantee that there's a number living there? The question is, what do we even mean precisely by that vague statement? And if we do know what we mean by that vague statement, if I were to give you a precise meaning, and I will be doing that, not today, Wednesday. When I give you that statement, then it'll be, how do you know that the number system does that? How do you know that there is a number system that is sufficiently rich that it fills the number line solidly? A third question might be, who gives a damn? Why is it important? Well, I want to tell you something, that without knowing that excuse me, I'm still sick. Without knowing that the numbers that we are aware of fill the number line solidly, in other words, without knowing that the number system is what we call complete, you can still talk about derivatives. You can still talk about integrals. You can talk about limits and continuity and all the stuff in calculus. But all the important facts about calculus that you've ever heard of and love or hate, I don't know, are wrong. They suffer from the effects of what is known historically as the paradoxes of Zeno. Who's heard of the paradoxes of Zeno? This guy Zeno asked some nasty questions in antiquity. For example, one of them, and you'll see this in the text. You're going to read it. I've got a reading assignment for you. There. Philosophical introduction to the number system. You know what? I've just been teaching Calc 1. I gave them the same reading assignment out of VCT. This guy Zeno said, when an arrow is shot from a bow, it can't reach the target until it has reached the halfway position. It can't get to the halfway position until it's got to the quarter-way position. Can't get there till it's gone 1/8. Following this reasoning to its logical conclusion, said Zeno, I can deduce that the arrow never leaves the bow. The question to ask Zeno is, would you be willing to stand in front? I think the answer might be no, hence the paradox, you see. These paradoxes yielded what is known as the first crisis in mathematics. It was a devastating crisis. It also came out in the form of the discovery of the 1 root 2 triangle. And some of you may have heard me say that the individual in the school of Pythagoras who discovered the 1 by root 2 triangle that we use in calculus to find the cosine of 45 degrees, that this particular individual suffered death by shipwreck as a punishment for discovering the triangle. His master, Pythagoras, was not pleased. And mathematics suffers tremendously from this type of paradoxical behavior unless the number system is complete. All sorts of statements. Let me give you an example. If you have a function defined on an interval, and the derivative of that function is everywhere 0, then the function, if the derivative is everywhere 0, did you hear me? Then the function must be what? Constant. Every little kid in Calc 1 knows that. It's not even true. It's not even true. All I have to do is make the graph snap at a point on the number line where there is no number living, and now I've got a function whose derivative exists at every number and is 0 there, and the graph is not the graph of a constant function. See?
Sneaky.
It's not even true. Therefore, the proof, whatever it would be if we gave a proof, would depend on the completeness of the number system. Because without that completeness, the thing is not true. You following me? So, wait, I need time. I need to say this. I'll come to everybody later. So the fact is that you have to ask exactly what happened. Well, let me tell you, if you knew your Calc 1, you might know that this fact is deduced from the mean value theorem. Very easy to deduce it from the mean value theorem. You might also know that the mean value theorem is deduced from a simple case of it called Raleigh's theorem. And you might even know, if you had a really good Calc 1, that Raleigh's theorem depends on a fundamental principle that says that a function continuous at every point in an interval with its both endpoints in must have a maximum value somewhere in that interval, which is a very hard fact. And that depends very strongly on the completeness of the number system. So calculus was in a total mess from its beginnings with Archimedes, as it developed through the centuries and blossomed in the 16th century with Newton and Leibniz, and described in such a spectacular way the motion of planets and the behavior of heat flow and all kinds of things, and everybody was so excited, but they also knew that they were talking nonsense. And towards the end of the 18th century, just before the beginning of the 19th century, an English bishop by the name of George Berkeley, B-E-R-K-E-L-E-Y. You will pronounce him Berkeley, you are wrong, it's Berkeley. George Berkeley wrote an essay rebuking the mathematical community. Who's heard me say this already? Yeah, you've definitely heard it, and you've heard it, and you've heard it. The set theory people, other than the set theory people, I'm actually saying something new, right? George Berkeley wrote this essay, and he said, look guys, I'm only a bishop. The standard of performance of me as a bishop doesn't have to be so high. You know? Dogma. You believe or you don't believe. I threaten you with punishment if you don't believe. You buy that message or you don't. That's my level. I've got no illusions. He said, but you guys, you claim to be better than me. You know what? You know better than I am. You mathematicians, your stuff is no more precise than mine. And the mathematicians were totally and absolutely stung. Incidentally, I want to mention that this guy Berkeley, he's the same individual as the one who said that if a tree falls in the forest when there is nobody to hear it, does it make a sound? He's that guy. You know, You've heard of this, you know? You know what he had in mind? He had an ulterior motive with all this. He wanted to say, well, of course it makes a sound, but if nobody hears it, how can you, in what sense can it be said to make a sound? He said his little message was, well, God hears it. You see, this was Berkeley's message. Buy it or don't buy it, I'm not getting involved in such questions here. Okay? Got myself into enough trouble. Right? I'm sticking with math. So I'll see you next time, Joan. Just pull it out. Thanks. So anyway, the fact is that the mathematicians were totally furious with Berkeley, and they attempted to answer him, and they could not. The mathematics was a total mess. In the year 1801, a German by the name of Bernhard Bolzano came up with a brand new idea. The definition of a limit. You kind of saw this in Calc 1. You think you saw it. We sort of waved the magic wand and we did limits and never said what they are. Some people in teaching Calc 1, they think they can explain it and they chuck a bunch of epsilons at you and you just about die. And then you realize after the first week and a half that this is going to go away. And so you heave a sigh of relief and you never see them again, right? You didn't see the definition of a limit in any meaningful way. Bolzano came up with a definition of a limit, and he was followed by Cauchy and Weierstrass and Dedekind and Cantor and Riemann and Darboux and there's so many. I'm not even thinking correctly. With all these names, I'm probably leaving out a whole lot. Abel, Dirichlet, Luhmann? No, I'm not that old. Right? So anyway, during the course of the 19th century, between the years 1801 and 1899, the paradoxes of Zeno were laid to rest with a solid mathematics that gave a precise view of what we mean by the completeness of the number system and why there is a complete number system. And the whole thing fell into place beautifully. And they were so proud of themselves. And in the late 19th century, approximately 1887, a German mathematician philosopher by the name of Gottlob Frege, F-R-E-G-E, wrote a book called The Foundations of Arithmetic. It was not meant for first graders. And in that book, the second volume of which appeared in the year 1901, slightly more than 100 years ago, in that book, Frege laid out the logical, solid connections making math work, the underlying arithmetic, so that the underlying calculus and everything else would work in mathematics. He was so proud of this book. And the second volume came out in the year 1901. And the second volume was being printed. The printing presses were running. And while the printing presses were running, poor old Gottlob Frege received a letter from a certain Englishman whose name was Bertrand Russell. No, Berkeley was long dead. You know, got rid of him. But Bertrand Russell, incidentally, if you read a biography of Russell, you will not be disappointed. It will not bore you, I promise. Very colorful character. Some of the biography needs to be written on asbestos. Anyway, so Russell sent a letter to Frege saying, look, I'm terribly sorry to have to tell you this, but I've stumbled on a little problem with Cantor's set theory. I have a paradox. Bertrand Russell's paradox. You know about it, and you know about it, and you know about it, right? And some others may have come across it. And Bertrand Russell's paradox destroyed utterly Cantor's set theory. And with it, the entire fabric of all mathematics. Nothing was left. The theorem 1 + 1 = 2 was gone. Because what does 1 mean? What does plus mean?
What is equals?
The equals is a little easier, but the 2 is problematic. Equals means the same object, as long as you know what you mean by the objects. That's the trouble. So the trouble is that Russell's paradox destroyed mathematics. Then in the early 20th century, they started over. And the set theory of George Cantor was replaced by a new, much more carefully written set theory that I have not yet taught to any of you. It's my second course in set theory. The set theory that came then was axiomatic set theory, very carefully laid out, and it's called ZF, Zermelo-Fraenkel set theory. It was created jointly by a German by the name of Ernst Zermelo and an Israeli by the name of Avraham Halevi Frankel. And together, these two gentlemen created the underpinnings of mathematics as we know it today. We are a long way from studying that stuff. We're not going to see it in 4381. Quite apart from 4381, you would need to do a serious course in infinite set theory before doing a course that involved this stuff. So most of you are a mile away from that. Don't feel depressed. We do things bit by bit in mathematics. Never look at the horizon. You might trip on a root. Okay, so anyway, just wanted to let you know. The number system, as we are going to view it in our course, is going to be a complete number system, and we're going to give a clear meaning about what that means. Roughly speaking, as a sneak preview, I'm going to say that you will think of it as saying that when you lay the numbers down on a solid number line, every point in that solid line is visited, is lived in, is occupied by a number. The numbers fill the number line solidly, and that is required for calculus. Now, I'm going to ask you to please read the philosophical introduction to the number system in 5.1. Okay? I especially took care to remove the exercises on surds that you see here, 5.1.3. Okay? And then I forgot to exit out when I put it here. Where was it? Somewhere. Somewhere. It sneaked in again. There. You see this? Exercises on inequalities. I want that out. I'm not responsible for those exercises. I was forced to put them in by reviewers of the first edition of my book, and the guy said he would not adopt the book unless his favorite problems were there. And some of them are waste of time. Now, I want to tell you about surds. So let me just make a new document, because I do not want you to think that this has anything to do with our lecture notes from today. Rational numbers are what? Fractions, right? And I want to tell you that little kids know about fractions. Little kids, really little kids, first learn about the number 1 and then 2, 3, 1 candy, 2 candies, 5 candies, yes? And they very, very quickly learn about fractions. The first time there are 3 kids and 5 candies, you have a choice between war and fractions. Okay? Kids know fractions. They also know negative numbers. Ask any little kid who has to use his allowance to pay for a broken window and he's got no money in his hands, right? He understands negative numbers. You don't learn that from some teacher in a school. You know long before. So now, what numbers do little kids not know? They don't know that there are any numbers that are not fractions, irrationals, right? They don't know that. But the fact is, there are numbers like that. If I were to mention the square root of 3, you would say, oh yeah, I don't know whether you're familiar with a little bit of arithmetical reasoning that shows that no fraction can be equal to the square root of 3 or square root of 2. So I'm not going there. I don't want to start messing with this. Not our course, okay? But if you were to ask somebody who is in the 10th grade, maybe even the 12th grade, show me some numbers that are not rational, and be as wide as possible. Show me the most wild numbers you can think of that are not rational. Well, the person would say, well, how about taking a fraction with 1 plus the cube root of 4, and underneath here, let's put the 7th root of 2 plus the square root of 7. Whoops. I will teach you on Wednesday. I'm giving you enough time to install Scientific Notebook, all right? I'm letting you know that on Wednesday I'm devoting some of the time of the lecture to talk to you about typing in Scientific Notebook. And I am very serious about this because all of you are going to be writing documents and sending me stuff for checking and for the purpose of asking questions. So right now I'm not talking about that. I'm dwelling on the mathematics for now. Anyway, should we do something? Let's put another radical on this, and should we make maybe a 19th root of that, and then maybe add something else similar to it, and then put another big radical? Oh yeah, I guess we could always make another fraction, you see? And you could make it bigger and bigger and bigger. How about making 200 million steps using plus, minus, times, divide, and radical signs? And any number you can make like that is called an SURD, a surd. And the family of surds is bigger than the family of rationals, okay? And I'll tell you something. Most people in the world have no idea that there are any other numbers at all. Well, if you went back to the days of Pythagoras, he had no idea that there were any numbers other than rational numbers. So at least you're one step ahead of Pythagoras. Okay. Yes?
How do you know there's more surds than rational numbers?
Oh, well, I mean, every rational number is a surd. So if there are, so immediately the family of surds includes, okay? So let's get moving. I'm going to tell you something that I can't prove for you. This number over here, this number, it's possible to prove that this number is not a surd. It's one heck of a hard theorem. You don't learn this in pre-calc. For this, you need to use a concept of things called Galois groups. Kind of cute things that would come out probably in a really good second course in abstract algebra. Goa, the father of everything that is important in modern algebra, died at the age of 21 in a duel. There's a bit of trivia for you. A number of these people died young. Niels Henrik Abel, whose mathematical contributions were so great they had to make a whole journal just for his work. That's named after Abel, and all kinds of other things named after him. Died at the age of 26. Joseph Louis Lagrange, whose concepts from calculus led to the most magnificent applications of calculus to physics, including quantum mechanics today. Did all his major work when he was 17 years old. Somehow, the tiny little fragments of contribution that I made, I was a bit older, I was in my 20s already. But anyway, just thought I'd mention this, all this to you. The fact that the cosine of 20 degrees is not a surd, well, you want to know another number that's not a surd? Pi.
I was thinking that.
E. The fact that E is not a surd is not terribly hard to prove. The fact that pi is not a surd is a real stinker. It's a really, really hard proof. What?
The golden ratio? Yeah.
No, that's a surd. Isn't that 1 plus root 5 over 4? Or root 5 minus 1 over 4 or something? Yeah, that's a surd. You want to know another number? How about e to the power of pi? It's possible to prove that that's not a surd.
ECI isn't.
Ah!
ECI is, rather.
E to the power of I pi is a surd because it happens to be equal to minus 1. I'm not going there right now. So anyway, just wanted to mention to you that the number system that you conceive in your mind is a tiny, tiny little sliver of the number system that needs to exist if you're going to conceive that our number system fills the number line solidly. Cantor put it in very dramatic language. He said the rationals are spotted in the number line, spotted like stars in a black sky. The dense blackness behind those stars is the firmament of the irrationals. On a dark, clear night, when you look up at the heavens, you might feel that the stars are very, very numerous. There's a lot of stars. Even in Genesis, Abraham is told, I will multiply your seed as the stars in the heavens. That was meant to be a good thing. He should have said, no, you mean I'm going to be a minority group. The fact is, the dense blackness behind those stars is immensely greater. The infinity of irrationals is, in a very important sense, greater than the infinity of rationals. To those who've done set theory, you know one way of interpreting it is uncountable, and the other one is countable. Yes? There's much more. In the theory of integration, there's more stuff I haven't told you about, because you haven't seen the theory of integration. You're not ready for it. So anyway, the numbers that you would think about if you included all these surds and every kind of number you've ever thought about, they make a few little spots and don't fill more than a trivial amount of the number line. The statement that the real number system fills that number line solidly is a very deep statement. It says, well, the number system is a lot bigger than anything you knew. It's big. Okay? All right. That's all I have to say about that. Let me just check my audio, because I'm getting a little bit. Was my other microphone, which I'm about to throw out. So anyway, rational numbers are fractions. I've got a few little exercises on rationals and integers here that I thought I would just mention to you before we move on. These exercises are very, very simple. Explain why this number here is rational. Would you like to see why this number here is rational? You know, it's an elementary school problem, because all you have to do is add these two fractions over the common denominator, 2 times 7. Isn't that right? You might even know that 2 times 7 is 14, but I don't know that kind of thing. And so what do you get? You get 3 times 7 plus 2 times 2. Well, the top of this fraction is an integer. The bottom is an integer, therefore this is a fraction, a rational. Okay? Right. I'm not doing this one. Okay? I don't want to insult you. Explain why 2.345 is rational. Answer. I'm not even writing it. I'll say it. 2.345 is 2345 divided by 1000. End of story. Explain why the sum, product, quotient, and difference of rational numbers must be rational. Well, see part A, right?
Closure of the rationals.
Yeah, I'm a little bit reluctant to use the word closure here.
Okay.
We could be running into deep trouble. We're going to be using that word to mean something else very soon. For each of the following statements, and we're going to vote on these, say whether you think it's true or false. If x is rational and y is irrational, then x plus y is irrational.
True.
I'm getting, how many people are voting true? I've got a certain number of votes. Who's voting false? I've got one vote. Okay, I think I'm going to call upon your proof first. Give an example. Or
I mean, honestly, I wouldn't know an example right offhand, but you know, since
you feel in your bones that I've got a sneaky example waiting to give you.
I don't know, I mean, you can go either way.
I'm going to give you a hint. I'm going to tell you that y is equal to x plus y minus x. Suppose this was rational. This one's given rational, right? If you subtract one rational from another, you get a what?
Irrational.
A rational. So therefore, if x plus y is rational and x is rational, the y has to be rational as well. So if x is rational and y is irrational, there's no way this one can be rational. See it? So those people who said true, you were right. I don't want to fuss about this. Part B, if x is rational and y is irrational, then x times y is irrational.
Not necessarily.
I'm hearing a no.
I can find a counter.
Who's voting yes? I don't have as many votes. I've got one vote for yes. Could ask you for a proof, but no, I've got to ask for an example, you see, to show that it can go wrong. You want to volunteer an example?
Counter example.
Yep.
If x is 0.
If x is 0 and y is,
Zero
take
number.
take
Pi.
pi or something, if you believe that pi is irrational, which is a heck of a hard theorem, by the way, let's take root 2, it's easier. See? Then the product being 0 is rational. See? So therefore, you can't guarantee. All right, I have nothing more to say about these problems. Okay?
I have one for third party as well.
But I want to get on, and I want to introduce a concept that will allow me to tell you what we mean by completeness of the number system. There are really two levels. One of them is, what do we mean when we say that the number system is complete? 2, how do you know there is a complete number system? Question 2 will not be answered in this course. We will take it as if it's been handed to us on a plate with watercress around it, and we'll work with it. One day, in a deeper or advanced course, we will say, why is there a complete number system? And I will show you, using the set theory developed of the Zermelo-Fraenkel set theory. That is my course in mathematical foundations. For now, I'm just going to tell you of a definition. And I'm going to say, here we go. Given a set E of numbers, convention, if I ever forget to tell you that a set is a set of real numbers, it's understood. All our sets are going to be of real numbers. If I ever want a set of chickens, I will tell you. I don't have too much use for sets of chickens. So anyway, given a set E of, and all our numbers are real, I'm not working with complex numbers in the course because we don't have time. I would have to tell you what complex numbers are. It's a long story. Given a set E of numbers and a number W, comma, we say, let me tell you something. If you are reading a mathematical sentence and you see this word, say, or write, or define, you know that you are looking at a definition. What is a definition? I spoke about it last time. A definition tells you exactly what we mean by something. You see? A definition tells you what a symbol stands for. It tells you what a word means. Okay? We say, given a set E of numbers and a number W, we say that W is an upper bound of E when no member of the set E can be greater than W. We're going to read this and chew on this statement a bunch of times. A number W may or may not be what we call an upper bound of a certain set. May or may not, right? What makes a number qualify to be an upper bound of a set? That no member of E can be greater than W, right? I'm going to say here, and I'll change color, the assertion that a number W is an upper bound of a set E, understood to be a set of numbers, is that the inequality x less than or equal to W holds for every x in E. For every x that belongs to E. For every member. The statement that no member of E can be found greater than W means that all the members of E have to be less than or equal to W. You understand? Less than or equals are permitted. You see? I want to tell you something. In the event that W is an upper bound of a set E, it is possible that W might actually belong to E. Might, right? W would be a member of E less than or equal to itself. You see? And in this case, W has to be the largest member of E. Is that a reasonable idea? Because no member of E can be greater than W. You see? And if W happens to be one of the members, then it's the biggest, because every other member has to be less, you see? So we have a little theorem here, not a very deep theorem and not a very interesting one. If you have an upper bound of a set and that upper bound of the set belongs to the set, it's the biggest member of the set. Okay?
Seems trivial, but it's really important.
Yes. Okay, well, I'm going to move forward from this, and I'm going to say, how would we make use of given information that a certain number, W, fails to be an upper bound of a given set E? That's my question.
We know that there's some
We've got a certain number called W and a set E, and I'm telling you that W is not an upper bound of E.
There's some member of E that's greater than W.
Well, yes, but how would you make use of this fact? Kim?
I guess you find that x greater than W, or find
I want to hear a particular line. You're about to write a mathematical proof. What's going to go? No. The information, and you're quite correct, and in a sense you're correct, but what you said is that you know that there must there must exist a member of E that is greater. So what do you write in your proof? You write choose. You write choose. This is what you would write. Here it is. Choose a member X of E such that X is greater than W. The information that W fails to be an upper bound of E is the information that there exists a member of E that is bigger. And when something exists, you say choose. Remember the mantra. When something exists, you say choose. To prove that something exists, you give an example. To prove for every, you say suppose. All right. Now, what about the idea of lower bound? Oh boy. I love writing with a computer. Given a set E of numbers and a number W, we say that W is a lower bound of E when no member of the set E can be less than W, right? Let's write this yellow thing here. The assertion that a number W is a lower bound of E. I feel so sorry for people who write on blackboards. It's their fault. I've been teaching people to do this for years. The assertion that a number W is a J lower, what's this? J Lewin, I've heard, right? The fact that a number W is a lower bound of a set E is the assertion that a number W is a lower bound of a set E is that the inequality, what? That there is no X in E less than W, so every X must be greater than or equal. Okay? So I've just told you about upper bound and a lower bound. All right? We are going to look at a little example. An example. Let's call it a little example. And in this example, we take E to be equal to the interval that runs from 0 to 1.
Is it a definition? We take.
Yes, that's a definition. I could have written, in this example, we define. E equals that interval. In this example, we write, W-R-I-T-E. E equals that. Okay? I'm going to ask a question. Given W greater than or equal to 1, true or false, the number W is an upper bound of E. True or false? I think it's obviously true, isn't it? Because if the number is greater than 1, it's greater than or equal to every number in the interval running from 0 to 1. Do you want to see a picture of this interval? I think I can do that. There you are. There's a picture. A quick and dirty picture. One day I'll tell you how I made that. I'm not going to tell you now. If a number is greater than or equal to 1, isn't it obviously greater than or equal to every number between 0 and 1? Okay. Now I'm going to say we assume that, W is negative. Now, this symbol in mathematics, by the way, is known as a negative sign. You ever heard of a negative sign? This is the only negative sign in mathematics. There is no other.
The other one is taken as.
We assume that W is negative. Tell me why W fails to be an upper bound of E. Here's the picture again. Given you a number that is negative, less than 0. Tell me why this number must fail to be an upper bound of E. Okay? I'm going to give somebody else a turn. Well, greater than 0. And then what? And then say that that number must be greater than W. You could improve that proof actually by being very specific about which number you're choosing, couldn't you? I mean, there's nothing wrong with what you're saying, but kind of heavy-handed. Kim?
0 and 1 are greater than W.
Well, I'm not too interested in 1. 1 doesn't belong to the set.
0 is greater than.
A number W less than 0 is not going to be within the set. So how can it be up or down if it's not even the set?
Say that to me again. I think I understood something good.
Any number W
Yeah, we've got a number W that is less than 0.
can't be an upper bound because it's
Can't be an upper bound of E because...
not in the set.
No, listen, 55 is also not in the set. That's not the reason.
There's elements of the set that are greater. There's less than even the smallest element.
Yes, I like that. Talk to me.
0 is less than even the smallest element. I mean, W is
W-
less than even the smallest.
Yeah, look here. You want to choose a member of the set to get it bigger than W. You're not wrong. But I've got a simpler proof. The number 0 belongs to the set, no? It's bigger than W. So you have in your pocket, you don't have to do any choosing. I know a member of the set, mainly 0, that's bigger than W, so W can't be an upper bound. Yes, sir?
Does W not have to be in the set in order to be an upper or lower bound? Because like the previous example, 0
Does
1,
W have to be outside the set in order to qualify?
set. Like
To-
outside the set, it couldn't be an upper bound or lower.
Well, we're talking about lower. I think,
Is it upper bound?
oh, we're talking about upper. In this particular case, I think you are raising an interesting point, but I haven't quite got there yet. I dealt with a number W that was greater than or equal to 1, and now I looked at this case where W is negative, and tell me why. I'm not going to write it. You tell me, all right? Besides, this is discussed in detail in the text. I'm just giving you the reading, but I think I'm coming to your question. We assume now that 0 less than or equal to W less than 1. This is a number in the set, right? Tell me why this number W cannot be an upper bound of E.
Because you can always find.
Tell me. I want to know how you want to choose. I need to know how you get it. You can write choose only when you know something exists.
I'll show you the input.
I've got a number W that belongs to that interval. 0 less than or equal to W less than 1. And I'm saying to you that this number W will not be an upper bound of E. And I want to know why. Right? I'm going to make you wait just a bit because I want to squeeze people to give me. Come on, folks. Yes, sir.
Because for every number W, you can choose an epsilon such that W plus epsilon is less than 1.
You can find.
I don't. You made a statement, but I don't understand it. I don't know why.
You're proving it by using it.
If you want to tell me that something can be chosen, I need to see an example. You can write choose only after you know it exists. I might agree that it exists, but I don't agree that you've told me why. Yes.
So let's choose that W is like 0.9.
You can't do that. You don't know what W is. All you know is that 0 less than or equal to W less than 1. You can't say, oh, well, I want W to be a half or something like that. You can't. You have no control. All I've given you is that 0 less than or equal to W less than 1. That's all you know. You can't, yeah.
I guess maybe like when the upper bound is, we know what an upper bound is, and W doesn't fit that qualification.
Well, I want to know why. I mean, you know, tell me why W can't be an upper bound. I want to know why it doesn't fit.
You can find a member of
Yeah.
a set greater than W.
Well, I want you tell me you can find it for me. You know, you claim you can find. I want to know. Talk to me.
She said the same thing, like, you can't find a number based on that. That's what I wanted to say.
Julie, I'm going to let you talk. I know you're going to burst if I don't.
Well, take the average, the arithmetic mean of W and 1. That's going to be between W and 1 and still be less than 1. So it's less
Here
than
is your
1.
proof. You can say, we observe that this number, W plus 1 over 2, yes, belongs to E, huh? And that W is less than this number. I had lots of people telling me that you believe that there's a point in that interval above W. And I'm saying, well, maybe you're telling the truth. I want to know why.
Show me a uniform.
You've got to prove existence. You've got to give an example. You don't have to do it this way, but it works. You see? Between here, look at the picture. We've got 0. We've got a piece of number line. We've got W. We've got a piece of number line. Let's not make it the same length. And we've got 1. And I've got a bunch of you telling me that you believe that there's some red stuff here. Well, if you want to prove that there is a number in that interval above W, you have to show me one. If you want me to believe that there is a unicorn, then you have to lead one in through the door on a string. You understand? Now, this is not the only way to do it, but it works. W plus 1 over 2 is bigger than W because it's less than it's bigger than W plus W over 2, since W is less than 1. See? And this number, the arithmetic mean of W and 1 is in the interval and bigger than W. That gives an example. That proves. Okay? Question?
So this is the whole arrow thing that you were talking about earlier, the arrow not getting all the way to, is that?
No, I'm not seeing an arrow here.
Oh, Zeno's paradox.
No.
I don't understand how you got W plus 1 is less than 2. What if W plus 1 was greater than 1? I don't know.
W plus 1 over 2 is a simple inequalities. It's elementary school, it's middle school inequalities. This
W
number
less than 1.
must be less than 1 plus 1 over 2 because W is less than 1. 1 plus 1 over 2 is 1.
Gotcha.
See? On the other hand, this number is bigger than W plus W over 2. In other words, the arithmetic mean of two numbers lies between them. Okay? So the fact is that we can prove that if a number belongs to the interval, that answers your question. See? In this case, a number belonging to this particular interval cannot be an upper bound of the interval, right? Another way to see it, by the way, is that an upper bound of this interval that belongs would have to be the biggest member. Does this interval Does this interval have a biggest member? It doesn't. Therefore, no member can be an upper bound. Okay? Now, folks, this is what I want you to do. I've given you some reading. I want you to read some stuff about the number system and a little bit about upper and lower bounds. It's in the text. Do a little bit of reading for me. I haven't spoken about all of this. I will speak about it. I will speak about some of this more next time. But try to understand the definition of upper bound and lower bound. Will you look at it in the text? Okay? Do this reading before Wednesday. Yeah.
My question is why we were not able to assign like the 0.9 and say that it's greater than W. Like why would you not assign just a number or choose
Well, what information was given?
W.
What information was given is that 0 less than or equal to W less than 1. For all I know, 0.9 could be smaller than W. I don't know anything about this number W. Okay? So if you need to show without knowing what W is, merely knowing that W was
Somewhere in that range.
in that interval, that there exists some member of the interval that's bigger. And we show that there exists one by giving an example. This example certainly does the trick. There are lots of other ways of doing it. All right, folks, I'm going to let you do some of this, and I will come back to this material. Who's volunteering today? Thank you.